All right, so we're on now to chapter 5. And chapter 5 is just one of these critical chapters in the textbook, at least for understanding what we're going to want to understand. And so I can't emphasize enough that, you know, I told you if all you really understood was chapter 1, you'd be going a long way towards electrochemistry. If you really need to, skip 2, 3, and 4, but read 5. And the reason is, and I don't know if we'll finish it today, because you can't scan if you don't understand how to do each step. So you say, well, we don't really do potential step methods, because I think that's the title of the chapter. You know, and so you say, well, we don't really do potential step methods. Why do I want to read that chapter? And yet you can't build a fundamental basis for cyclical chemistry without learning what happens when you step. I also want to emphasize, again, those of you who will be ever taking an exam with any professor in this department, that many, many times during an oral exam I have heard somebody say this. I can't really understand what's really fundamentally happening with this game. Let's just simplify it. What if you just step to this voltage? What would happen to your electrode, right? And so you know, professors love to simplify. They don't want to talk about scanning because that's too hard to talk about. So they want to talk about this stuff. And so I get people get asked these type of questions all the time. So that's why it's sort of fundamental that we understand it. Okay, so this chapter, though, in the first paragraph or something, sets out some rules. So the rules of the chapter here is that the only mass transport is diffusion. So that's the rule. You're only going to look at potential step methods. And the last one is one that you wouldn't really think about. But they're going to talk about only things with a small a to v, that's a big V. I was kind of like word volume, area of volume. So what this means is that your electrode area is small compared to the volume of your sample. And that essentially means that you can't use up your sample. You can't change the whole concentration, you can't use it up. So there's not going to be sample limit, you know, here. There's going to be an infinite amount of stuff in solution that you could theoretically look at if it could only get to the electrode. Those are the conditions. Okay, so let's look at a basic step experiment. All right, so we're going to look at potential on this axis, and we're going to look at time on this axis, and we'll call that time 0. And so you're going to step from some holding potential E1 to a second potential we'll call E2. Now in the book, remember, they love reduction. So they're doing a step to a negative potential to a reduction. But the theory is all the same, whether it's positive or negative, if it was oxidation or reduction. But just so you know, we're on board with the fact that everything loves the top reduction. All right, so at time 0, we make our step. And then we're going to look at what happens at different times after that. So we'll call those like times 1, 2, and 3. So what's happening to our current as we get out there. Okay, so we can make a graph then, when we do that, of the concentration of our species. Actually, that's not time. Let's look at that. Sorry, this is our electron. This is concentration. That's distance. The next graph, give me some time. So we want to look at the concentration. So we're going to start with some volt concentration. I'll put a degree on because somebody brought me cold markers, so I should use them. So we'll have to start with some sort of bulk concentration, right? So that's the concentration in solution. And we're going to assume that when we're at E1, we're going to kind of assume that we're not doing the reduction. Right, so the E1 is not sufficient to do the reaction, but E2 is. So we're going to step from something, not doing anything to something that we can. So over time, right, what will happen? So this one would be, right, the curve for T is equal to 0. And over time, the concentration of, so I'm doing this on purpose. I didn't draw this earlier. I kind of skipped over it. We're going to assume, right, if this is sufficient to do the reaction, that we're going to drive the concentration to 0 at the electrode surface. So all of those should be kind of like 0 to 0. So at time 1, this might be the concentration profile. So again, because I can react it here, right, I use it all up, so it's 0 at the electrode surface. As I get further and further away, though, it returns to the baseline concentration. And over time, my diffusion profile kind of grows like this. Right, so over time, my depletion layer, where there isn't any analyte because I'm not stirring, because I told you I was only going to have diffusion, grows out over time. And so, if I kept going, the T's, it would look like that, right? It would continue to grow out over time with the diffusion coefficient, equations that we learned. We can do one more graph, then. That's lovely. It tells us about concentration. But what are we actually probably going to measure, right? We're going to measure I as a function of time. And so I, right, at 0, we're going to have no current. So see that? At 0, I have no current, right? When I step up, I'm going to get a spike in current, right? Everything that was at the surface is going to immediately be reduced in this case. And over time, the current's going to decay. What's this decay? I want you to talk to me in terms of math now. What equations have we been learning about diffusion? Right, so diffusion is what controls how much gets there. So, right, this drops off, right? Because not enough stuff can diffuse. It's dependent on how much current you see, depends on diffusion. So what kinds of equations were we learning for diffusion? Hopefully somebody has learned equations for diffusion. I say my favorite diffusion equation was square root of 2 dt, right? So we just did this. Square root of 2 dt. All right, so this is obviously t to the minus something, right? Because it's a decay. But yeah, it's t to the minus 1/2. That is a t to the minus 1/2. Decay in I. It's not exponential. Lots of times, do you have any curve that goes like that? I was expecting someone to guess exponential. But it's not. It's a t to the minus 1/2. And it comes because diffusion is what is delivering stuff there. Diffusion goes on the t to the 1/2. And so it ends up being it's not exponential decay. It's a t to the minus 1/2 decay. And so, again, we'll talk scan rate probably a little bit tomorrow, but this is what everybody thinks. Again, you should be able to pull out. So someone says, well, what if you just step the potential? What would current look like then? You need to be able to draw some sort of curve like this, and then rightly say, oh, this is a t to the minus 1/2 decay. Well, why is that? Well, diffusion. It's t to the 1/2. As we're decaying, it's just a t to the minus 1/2. If you can pull out things like that, then you sound like you kind of have it under control, right? They understand, where these things are kind of fundamentally coming from. So in our little world, we call this experiment chronoampherometry. But I say that so that you can read papers. So there are people who do chronoampherometry instead of FSCB. maybe tomorrow we'll talk about, well, if we finish today, we'll talk about the pluses and minuses of coronary hyperometry compared to C. But I have never, ever, ever sat in an oral exam and heard anybody ask them to tell them about coronary hyperometry, right? Instead, is that they put the question like this: oh, scanning's kind of hard. Can you show me what the current would look like at your electrode? We just say step to +1. You know, so they ask it in terms of just doing a step equation. Is that I've never heard anybody use the word coronary hyperometry in an oral exam. But as you go to read scientific literature, you know, and you read a paper and they're doing coronary, I read a coronary paper recently. I don't know if I was reviewing it or what. You know, I mean, you've got to have some idea. Oh, I know what that experiment is that they're doing. Okay, so now what happens if we stir? All right, I'm going to break my condition. But all right, so we'll do our 2 little steps as we go there. And so, you know, now if we're stirring, I'm just putting another room, sorry, I'm not putting this on this time. The concentration distance plot is going to look different. So the concentration versus distance plot, again, is going to have, this is why I didn't draw it earlier because I knew I would draw it. Right, we're going to count this nerve perfusion layer. And if we're stirring, right, the rest of it's going to be kept in the bulk, right? So up until the nerve perfusion layer, we're going to get the bulk concentration, and that's not going to change over time. So the only things now that are going to change over time, right, are going to be these. And these ones, well, I don't know, we can do arrows. So this is going to change over time, and eventually, right, we're going to drive the concentration to 0. And once it's to 0, right, we're going as fast as we can go. We can't go any faster than having 0 concentration at the electrode, right? We can't get it there any faster than this line. This line ends up being the fastest that it can get there. There is a condition, however, so if we did that, let me finish. We would get a plot, right, that would look like this. And when we're going as fast as we can, we call that the limiting condition. That's our limiting current. And I gave you a quick limiting current earlier, but when we're going as fast as we can, that's called the limiting current. And so, again, once we get here, and it might take us a little while to get there as far as potential, but we would get that. Okay, so let's think about then, I can't get this graph though from that experiment. I just see that, right? So I could get you an I versus T, right? And so the I versus T, right, is going to look something like, right, where it's going to be essentially the same thing I showed you over here. That it's going to decay down. But it's not going to decay, as I said, quite as fast as that one because you're going to have stuff coming in. Well, I can't, I skipped ahead to show you what a roll tamarind looks like, but I can't get that from one experiment. So with potential step then, they have this sort of theory of sampling. And they say, what if instead of just doing one little step, I did a series of steps. So I come back each time with the same thing. You know, and I'm going to do steps 1, 2, 3, 4, 5, something like that. So I'm going to step up, come back, and step up a little further, come back, step up a little further, come back. we kind of look at I over time. Yeah, we'll call this T0. It may be that when you do this first step, what if potential 1 is not sufficient to do the reduction, right? So if it was not sufficient to do the reduction, meaning we just thermodynamically aren't there, right? We don't have enough energy. We haven't gotten the molecular orbital to the energy level we need to transfer the electron, reviewing all the concepts we want to know. Right, then we would get nothing, right? So nothing says we have to get current just because we stepped. If we don't step towards dimension sufficient to do anything, we get nothing. So, you know, often don't remind yourselves of that. Okay, but like, you know, by the time we get to 2, let's say, you know, we're able to do it. But maybe at 2, right, we can do the reduction, but we're not able to do it at the full rate. So remember, now we're going back to kind of the kinetics thing. But remember, I was related to E minus E, well, there was that E minus E0 prime sort of thing. So it depends on how close we are to the formal potential. If we're still real close, we might not be getting as much current. And so if that was true, right, we would get a small current, maybe for 2, but it would disappear. And then, you know, what if, you know, now we go to 3 and 3 is even higher, maybe, I can't do the reduction at the full rate. You know, we're going a little faster, but maybe we're not still quite fast enough. And on 3, we kind of come like that. And then we go to 4, and let's say that finally we're at 4. Now we're at the, we're high enough that we can do the reaction as fast as we can. There comes a point we're going higher, just something to help the cause. And so we're there. And so, you know, 4 would look something like this. And then if we were to put 5 in there, 5 is going to look the same. So you're going to get to a point where you just can't go any faster. And so what you would do then, right, is maybe pick a point in time. So let's pick a point in time. We'll call that tau, right? So now we can sample what's our current look like at that point in time. And now, right, I can say, well, that's going to be a function of voltage, right? And so I said, oh, at time 1, voltage 1, 0.1, I got 0. And now here at point 2, I have a little bit more, and 0.3, I have more, and then I get to 4 and 5, right? It literally goes off to the limiting current, right? If I did enough of those, right, I could theoretically make that curve. So this again is what people traditionally know. Again, we'll talk next time about linear sweep. Right, but this is what people would say a traditional linear sweep voltammogram is. But it all basically comes from the idea of I step a little bit more, and I step a little bit more, what would I get if I looked at a given time? And so again, you can kind of have this come in, and again, that's our limiting current. This is all, again, with some sort of stirring. So sometimes people will call this, did I write that down? Maybe not. Sampled voltammetry, or even normal pulsed voltammetry, normal pulsed voltammetry. My postdoc advisor, who was a neuroscience, used to claim this. He said, electrochemistry just should be so simple. There's only a couple variables, right? There's E, there's I, there's charge. You know what I mean? Like, there's not that much to it. It always astounds me how each one of you electrochemists can somehow seem to invent their own electrochemical technique, give it its own name, and then refuse to do anybody else's technique, thus making, you know, all papers uncomparable. Well, that's not exactly true, right? But you know, there's probably at least 100 different techniques in electrochemistry, and no, I don't know the names of them all. But we'll learn a few of them kind of as we go along. But there was some truth to that statement, that everybody does their own, has their own little way of pulsing the voltage, and now so you can't compare your results to anybody else's. Okay, so right now, all we've ever done is step up, but we haven't stepped back. So let's go ahead and do that. All right, so now, all right, we're going to do it. We're going to go up, and we're going to go back down. Right, and so as we do that, and we're going to look at I over time, right, time 0, we'll call this tau. At time 0, right, we get the current going up, right, and it's going to decay back down, and at time tau, it's going to go, like, we're going to, you know, switch back and do a reduction. Well, if this was a reduction, we'll do oxidation, or vice versa, you know, and that will go back that way. So that's what you would get as far as current goes. You do the 1, it would decay. It may not decay to 0 if you don't give it enough time, and then you get the current in the opposite direction. And so this is, again, often called double potential step chronoamperometry. I don't even know that everybody uses that term. Quite frankly, almost all the chronoamperometry you will see reading literature for our purposes is a double potential step. Nobody just steps up. They always step back. It's a little hard because if you don't step back, like think about this experiment. Intrinsically, you have to step back at some point. Right, you know, I didn't show it to you, but you had to be able to start over to do 2. So the question is not whether you step back, but whether you choose to collect the data and do it. Right, but you got to step back to start over. So that's if you're going to step back anyways, you have to collect the data. Thus, almost every kind of thing. As far as that goes, it's possible to not just do